Hello and welcome to my small series about computers. In this episode we will take a look at the construction of a computer from individual transistors up to a whole CPU. We will also see how a CPU works and how we can give it commands. So stay tuned for awesome tech stuff. Understanding a computer isn't that complicated. It's just as easy as moving your body. When you were younger, you probably were wondering how you can move your body, but you didn't know the answer, so you probably thought of something like magic. Later you learned that we have muscles which can tense and relax, so let's go under the skin and take a quick look at them. Basically, a muscle is made up of a bunch of fascicles bundled together, which are by themselves just made up of a bunch of muscle fibers, but even they are made up of a bunch of myofibrils. So ultimately, a muscle is nothing more than a bunch of strings that are bundled together and then bundled again and again. Or just a bundle of a bundle of a bundle of myofibrils. Let's go back to computers. After all, this is what this video is about. But aren't they human after all? However, it's the same principle for computers, but with fewer bundles and more circuits. The smallest component of a computer is a transistor, and if you combine a few of them, you can build new circuits which can be used to create even more advanced circuits until you made a whole computer. Essentially, a transistor is nothing more than a switch. Not that switch, couldn't they choose a better name? If it's activated, current can flow, and if it's deactivated, current cannot flow. It consists of three connections called base, collector, and emitter, and a semiconductor. All three electrodes are connected to the semiconductor, which sometimes conducts and sometimes not, hence its name. But with the base electrode, we can control the semiconductor, just like flipping a switch with your finger. If enough voltage is applied to the base electrode, current can flow between emitter and collector, just like a dam can control the flow of water. So you may ask yourself now why we need simple switches to build a computer. First, you can fill long Wikipedia articles with them. Second, they can switch billions of times per second. And lastly, you can build pretty awesome stuff with them. For example, if you put billions of transistors together, wrap them with plastic, and put a display on top, you can build one giant switch out of many tiny switches. That show got pretty old soon, but I won't switch that running gag. Or basically any other computer. But let's start with way more primitive circuits. What could be better than one transistor? Two transistors. Let's put one behind another and voila, you just made a breakthrough in computer science by inventing the AND gate. Now we can create a truth table for all inputs and outputs. This fancy circuit only conducts electricity if both bases or inputs are activated. If both or one input is deactivated or false, the output is false too. Totally not confusing. Let me clarify things a bit. Current is the flow of electrons from one place to another. In computer science we say 1 to electrons and 0 if there isn't any current. And when we are talking about logic gates which perform logic operations like our AND gate, we use the terms true and false instead of 1 and 0. So there are just a few different terms that flow down the river, but they all mean basically the same. There are more logic gates that we can build. If we can put them behind each other, what could we also do with them? Why not put them next to each other? And again, we build a new logic gate, the OR gate. Current can flow if any of the inputs are true. There's one more logic gate left that we can build with two or fewer transistors. In fact, we need only one transistor and a clever trick, like the criminal who's just stealing your wallet. Instead of using the collector as an output, we add an extra wire and use it as an output. If the transistor is deactivated, we get true as an output, because the electrons don't have any other way. But if we activate our transistor, the electrons flow to the collector because they are lazy and don't want to go a detour. Therefore, we get false as an output. The NOT gate converts every signal, just like a criminal trying to turn false money into real money. There are 4 more logic gates, but we'll only take a look at one more, the exclusive OR gate. Actually, we won't take a look at its construction, but we will take a look at its truth table. Aren't these logic gates awesome? Still boring? Then it's time to use multiple logic gates to build even more complex circuits. But engineers are lazy like mathematicians. They say 3 times 4 instead of 4 plus 4 plus 4. I can't even write pi out. It's a cake word, just P-I-E. Remember our muscle from the beginning? You put a bunch of myofibrils together and called it muscle fiber, so we don't have to care about individual myofibrils. And we do the same with transistors. Mathematicians have a special symbol for multiple additions, and we have special symbols for our logic gates too. A long D for an AND gate, a pointed D for an OR gate, a triangle with a dot for the NOT gate, and a pointed D with a curve behind it for the exclusive OR gate. This principle of putting smaller parts together to create a new unit, so you don't have to care about individual parts, is called abstraction. This principle is important in computer science. Or do you want to build a modern CPU like a giant puzzle out of billions of transistors? For us, it's time to move to a higher level of abstraction and say goodbye to our beloved transistors. It's time to build something that can actually calculate for us. Let's start with the simple addition of two single-digit binary numbers. The table would look like this. 2 isn't a binary number, so we use the same trick from our decimal system. If we have no numbers left, we put a new digit to the left side and start again. If you compare this table with the tables from our logic gates, can you tell me which two logic gates do we need? One exclusive OR gate for the first digit and one OR gate for the second digit. This circuit is called half adder. Why half? Well, because when you add two numbers, you have to add sometimes three numbers at once. Let me give you an example. Let's add 1, 1 and 1, 1. We want only one output per digit, so we move the 1, also called carry bit, to our next digit. But now we have to add three numbers, which our half adder can't handle. We need a new circuit. Let's move up to a higher level of abstraction and use our new half adder to build a full adder. We can use one half adder to get the sum of B and C, and another one to add the sum of B and C to A. Then we need only one OR gate to check if any half adder has a carry bit. We can move to an even higher level of abstraction and connect our full adders. Now we can add any 8-digit binary numbers faster than mental arithmetic. If you want to build a machine capable of adding, multiplication, subtraction, and division, we only need a new circuit which can subtract, because multiplication is just a series of addition, and division is subtracting until the leftover is smaller than the divisor. To keep things simple, we use a bit of magic and create one. That's all we need to build the heart of a CPU, the arithmetic logic unit, or ALU for short. An ALU has a bit more functions than just addition and subtraction. For example, we can add or subtract 1, can apply AND or XOR logic on every digit of two numbers, and even more. The cool thing about the ALU is that we can control which operation it performs. Therefore, we need three inputs, 2 for our numbers and 1 to specify which operation should be executed. It has two outputs, one for the result and the other one for additional information, like if our result is 0, negative, or too large for our ALU. If we add 1, 0, 0, 0, 0, 0, 0, 0, and 1, 0, that's just the same number, with an 8-bit ALU, our result would be 0 because the 9th digit gets cut off. But the other output gives us the information that the overflow flag and the 0 flag was activated. A buffer overflow is like trying to get as much as possible in your luggage, but once it's full you can't add more, your luggage could explode. You have to leave the rest at home or get a bigger suitcase. So if we want to give our ALU instructions, we need an opcode. Our opcodes could look like this. So if we give our ALU the opcode 0100 and these two numbers 000010110 01011101, we get 01100111 as a result. Great, but we can't do multiplication and division or more than one instruction without having to give new inputs. It's time to move once again to a higher level of abstraction and build a fully working central processing unit. We need to connect our ALU to a control unit, give it a few registers to save interim results, and lastly we need to connect it to RAM. The control unit receives our commands and then decides what our ALU or RAM has to do. RAM means random access memory because we can access its data in a random order, unlike tape drives, CDs, or DVDs. It's also a volatile memory, which means it loses its data when it's not powered. That's why you always have to save your data when you are working on it. The power could go off or your computer could crash. If we want to give our CPU instructions, we need to know its instruction set in the first place. Ours could look like this. It works like the opcodes from our ALU, but is a bit more complicated, so let's go through a program together. Oh, we don't have one yet? Then let's write one together. Let's start with a very simple program, adding two numbers together. First, we need to get our numbers from our RAM into the CPU's registers, so we need to specify where we want to save them in our RAM. Let's use the two last memory locations for that. So the first two lines of our program are made up by the opcode and the memory address. For our third line, we need the add opcode and two register IDs, which could be the following. Now it's time to save our result into RAM. Our result was stored in the second register from our addition, so we need its store instruction, and let's use the memory address before our numbers to save it. Wait, our program isn't finished yet. We need to stop it with a halt instruction. So let's run our program now. The control unit recognizes the load A instruction, so it tells the RAM to load memory location 14 into register A, which has now the information 01001110 or 78 in decimal. The same thing happens with the next instruction, and register B holds now the information of memory location 15, 10100100, which is 164 in decimal. Now our control unit understands an add instruction and adds the two registers with the IDs 01 and 10. Our results get stored in the second register, and B holds now 11110010. Next, the store B instruction is being executed, and memory location 13 stores now 11110010 or 242 in decimal. Now the control unit gets the halt instruction and stops our program. In the early days, results were printed on paper, but today they are displayed in a console or even a GUI. Congratulations, you wrote your first program in machine language or machine code. But today only very few programs are written in machine language. Machine code has the advantage that computers can read them with ease, but not humans. Could you tell me which bit I flipped? Finding mistakes or bugs in machine code is very hard, so programmers needed a way to code faster and with fewer bugs. They needed a new language, and that's what we'll discuss in the next episode. Let's summarize everything so you can remember it better. The transistor is the smallest part of a computer, and it works like a switch. The other switch. We can control the flow of electrons with it. If we put a few of them together, we can create some logic gates capable of basic logic operations. With these logic gates, we can build circuits that can do addition, subtraction, or a hell of a lot more. If you put these circuits together with more logic gates, we can build an ALU which can do addition, subtraction, and more, like bitwise logic operations. When the ALU is connected with a control unit, some registers, and RAM, it becomes a CPU. We can load our programs and data into RAM. The program is written in machine language, which consists only of ones and zeros. The instruction set contains all commands our CPU can execute, and that's how a computer works without going into too much detail to make it enjoyable and understandable for humans. Just imagine what would happen if we take the next step and start connecting computers together. I hope you learned something about computers and muscles. Your biology teacher would be proud of you. Thanks for watching. If you're interested in computer science or programming, I can really recommend this crash course about computer science. It really helped me a lot to make this video possible, and it covers this topic with more detail and historical context. It also features topics that I haven't and won't talk about in the series. And it has some nice animations too, but isn't fully animated. So you have to see another human being talking to a camera. If this still is not appealing enough to you, I will link a computer science playlist somewhere. See you in the next episode, when we will discuss programming languages.